Afternoon, everyone. Today I will talk about my project 2, Evolving with Machines, Simulation and Optimization of Charthouse Daylighting Performance. My project 2 examined the daylighting performance, simulation, and optimization of Charthouse. Charthouse is an iconic structure within the former Imperial Sugar Company complex in the Sugar Land, Texas, often described as the last classic charthouse in the United States. This project focuses on the daylighting performance of Charthouse and employs genetic algorithm tools to explore optimization possibilities for its interior lighting. It aims to guide adaptive reuse decisions through parametric optimization while respecting the constraints of industrial heritage. And the fifth and the sixth force were selected as the research targets primarily because they feature a unique overhanging space connecting these two levels. And secondly, the floor between them incorporates numerous circulate openings reserved for connecting production equipment's pipelines. Thirdly, this interconnected space is one of the Charthouse defining characteristics. During subsequent adaptive use, it can be converted into a public space. And the daylighting simulation was performed on the original model, as the result shown in the figure below. Under the LM83 standard is SDA value, which is 92%, indicating excellent natural daylighting performance. However, the ASE value, which is 58%, and is far exceeding the acceptable threshold of 10%. So to address this outcome, the project introduced external aluminum louvers to optimize daylighting for Charthouse. Here, these are my components. So by applying the logic of dividing contour lines, each window was segmented, and extruding these contour lines yields the aluminum louvers used for simulation. And the logic employs only two sliders to set the parameters. The number slider controls the depth of the blade, which equals the division distance of the contour lines. And this logic ensures the consistent blade's dimension across windows of a variety size and maintaining the visual coherence. And the angle sliders controls the rotation angle of the louvers. And also to achieve a solution closer to the optimum, the project incorporates a genetic algorithm. The Galapagos within the Grasshopper serves as the computational engine, and the number slider and the angle slider function as the genome, while Python code defines the fitness function. So this code calls the SDA and the ASE numerical outputs from Climate Studio simulations. And under the LM83 standard, SDA is treated as the primary optimization objective, while ASE is subject to an upper bound constraint. So if the ASE exceeds the maximum acceptable range by 10%, a penalty will be applied, a deduction calculated as the percentage overrate multiplied by 5.0. So this forces the Galapagos to prioritize the solutions that both enhance the SDA and keep the ASE within the reasonable limits. So the penalty weight of 5.0 references common penalty function settings in multi-objective optimization, ensuring the magnitude of the penalty matches the primary object's scoring range. The project underwent 2 rounds of computation. The initial round of work is designed to rapidly validate the feasibility of this workflow. And compared to the first round, the second round's both population size and the iteration count were increased to obtain more comprehensive results. We can see that the external louver system effectively balanced the natural daylighting and the glare control without alerting the original facade composition or industrial texture. So this transforms the previous severe overexposed industrial space into a more suitable and comfortable indoor environment. And this is the picture that generated by the Gemini, and this is the Python code. Thank you. This is my presentation.